So one of the things to do next is I want to look at, so this is chapter 6, I want to look at matrices of linear operators. Okay, so I want to think about if I were to have a linear transformation, let me say linear transformation rather than operators. But if I were to have a linear transformation, it turns out that we can describe all linear transformations as a matrix, and it turns out that every matrix corresponds to some linear transformation. So in a certain sense, matrices and linear transformations are the same thing, just kind of different language for it. But at the heart, at the core, they really just mean the same thing. Okay, so for example, just to pick, I'm going to start easy. Let's say I have in R2, our transformation, so this is going to be, let me use the notation that we've developed. Let's let t go from R2 to R2, given by t of xy is equal to 4x plus y, 2x minus 3y. And this is just nothing other than multiplying xy by the matrix 4, 1, 2, negative 3. And this is our matrix that gives us our linear transformation. So in a certain sense, this linear transformation is nothing more than just multiplying this matrix, multiplying this vector xy by this matrix 4, 1, 2, negative 3. And if I were to have sets, so if I were to have two vector spaces of varying dimension, I would get same thing. I would get a matrix here. It just wouldn't be necessarily a square, or it could be whatever size we need it to be in order for this to take Rn to Rm, right? It would be m by n in that case. So we could also look at, say, a matrix from R3 to R4, where t of xyz, okay, is going to be, let's say it's going to be 4x plus y plus z, 3x plus y plus 4z, 1x plus 5y plus 9z, and then negative 2x. Okay, so we could also think of this as this linear transformation. This is going to be the vector x, y, z, multiplied on the left by the matrix 4, 1, 1, 3, 1, 4, 1, 5, 9, negative 2, 0, 0. Okay, this is a 4 by 3 matrix, which makes sense because we are mapping R3 to R4. So if I multiply by a 3 vector, I get out a 4 vector, right? So if I were to multiply, if our input's a vector in R3, our output's a vector in R4. Okay, so that's matrices of linear transformations. I really don't have too much more I want to say here. Really just one other idea. And this is an idea that we actually talked about in the first 2 weeks of class, maybe, somewhere in that area. But let me remind you of something. So if I take a composition of two functions, let's say I have a function f and I have a function g, then the composition of f and g, so f composed with g, is just f of g of x. And so what I want to do is I want to think of transformations where we have matrices that we can write our linear transformation as. So I could have written this as, say, t of xy. So t of xy, I could write that as, say, a times xy, or even more to the point, let's call this vector v. So t of v is av, right? That's kind of how we're going to think about our linear transformations. So let's say that I have two linear transformations, t of v, which is av, and say S of V, which is BV. Okay, and let's just for convenience say that T and S both map Rn to Rn. Okay, so they have the same input and output size. We don't really need that. But what I want to do is I want to find the composition T composed with S of V. And so we know by definition that this is going to be T of S of V. And S of V we said is BV, so this is T of BV. And T is just, you take your input and you multiply on the left by A. So this is A times BV, or really this is AB times V. And so it turns out that matrix multiplication really is nothing more than composition of two linear operators. Right? Clearly we couldn't say this exactly the first 1 or 2 weeks of class, but we kind of checked that matrix multiplication and composition were the same algebraically. Okay, we did do that in the first couple weeks. So matrix multiplication and composition really are the same thing. That's why matrix multiplication works the way it does, so that this is true, right? So that matrix multiplication is composition. Okay. And I should just point out that in general, if you were to have, say, f of x is, just to make this up, say x squared plus 1, and g of x is, say, 3x plus 4, I want you to notice that f composed with g and g composed with f are not the same thing, right? F of g of x is 3x plus 4 squared plus 1. And g of f is going to be 3 times x squared plus 1 plus 4. Right? And so those are clearly not going to be the same thing. Look at, say, the, whatever. It's pretty easy to see that those are not the same thing. Right, on the left, there's a linear term. On the right, there's not, for example. And so what that tells you, what that kind of reinforces, is that in general, composition of linear operators is non-commutative. So in general, if you were to have two linear operators, T composed with S, then T composed with S and S composed with T are in general not going to be equal. And we know this already because we know that if I were to take the product A times B, that's not the same as B times A. Okay? And so that's really the point here, is that matrix multiplication and composition are really equal. Okay? Other than that, we could think of every linear transformation as a product, a matrix product.